snow we got as a reminder that winter
got
is never
snow?
far from Minnesota. Right, so the plan today is to finally finish talking about equilibrium. And then, if we have time, to begin one of our next topics. So the plan today, actually, for the equilibrium is just to go through another couple of examples that I think are really useful to hold in mind. They serve as a good review of everything that we've done so far. And good news, they're actually easier than the things we've done so far. So the plan is to explain them to you. And before I forget, I often try to stay for like 10 minutes after the lecture and like try to answer people's questions. Today I have to run when this lecture is done. I'm very sorry. But unless there's some true emergency, I would prefer to be able to escape right after the lecture. As usual, I'll stay after the lecture on Wednesday. So let's talk about equilibrium and related topics. So just as a reminder, since you had a weekend to forget everything about physics, at least I did. What is torque? So torque is like the analog of force that makes things rotate, just like force is the thing that makes things move, more precisely accelerate. Same thing with torque, that makes things accelerate. The torque is R cross F, and its magnitude is the magnitude of the force times the magnitude of the radius times the sine of the angle. We've said that before. One thing that came up during office hours today is I heard a rumor that many of you might appreciate a review of cross products and right-hand rules. So I'm going to take the view that the very biased office hour sample that I had was accurate as a prediction of what people want. I'm just going to inflict a review on you of cross products, even if you didn't want to hear it, but it won't take very long. So I said up on the slide that torque is R cross F. So let me draw a couple of pictures and show you how to figure out the direction of the torque. So let's say I have a spinning disk like this. The axis of rotation is like this, okay? And let's say that its radius is R, and I apply a force right here, F. Now, actually the way that this is drawn, it's actually not what I want to do. This is 3D drawing is something that I leave to those of you who are good at art in the room. So what am I trying to communicate with this drawing? I have a plate, okay, that's spinning like this, okay, and I'm pushing on its edge, and it's spinning like that, and the force is into the board. Does that make any sense? That's what I'm trying to say. So in this context, somebody could ask you, some evil physics professor like me, could ask, well, what is the direction of the torque? Okay? Due to this force. So what would you do to figure this out? You would first have to figure out what is the vector R. Like, where is it in this picture? So the way to think about that is the vector R is a vector drawn from the axis to the place where you apply the force. This is like always true. That's how the R's are defined in these problems. And that's what it looks like. And the magnitude of the vector R is capital R, the radius of the disk, in this case. Is that clear? Okay, so just for posterity, the magnitude of the torque, which is the magnitude of this, which is r, times the magnitude of this force, which I'm just going to call F, times sine of the angle between F and R. If you think about what this angle looks like, we have a vector pointing that way and a vector pointing straight in. The angle between them is 90 degrees. So this is 90. So sine of 90 is 1, and so this is RF. The question is, where does tau point? So the way we do this is we take our right hand, okay, step 1, pointer finger, we put our pointer finger, this one, in the direction of the first vector. What do I mean by first? I mean, I'm trying to figure out what this product is, what this cross product is, and the first vector that appears in it is r, and order matters. So r. So r points that way. Okay, so I just accomplished step 1. Step 2, allow your middle finger to point in the direction of the second vector. So how do I do it here? So I point that way, and I point my middle finger into the board. I don't know if you can see it. This is what I'm doing. Okay? Now you can't, so I'm going to tilt it just so you can see what I'm doing. Okay? And now, if you tuck in the rest of your fingers and just let your hand relax, more or less, you will discover that your thumb points, in this case, up. And that is the direction of the cross product. Okay, so that's how we do it. So now, just to make sure that we're on the same page, let's say that we had same situation. Here is R, and here's a force F, and now it's coming at you. And again, we want to know the torque. Which way does the torque go? So I'm going to do it again. I'm going to point my finger in the direction of R. I'm going to let my middle finger come out, and now I need to turn it in the direction of F. And now watch out, I better not change this direction as I do it. So I have to twist my hand, possibly seek physical therapy, and you will discover that now that my pointer finger is pointing at you, this is a lot easier for most of you who are younger than me, you will discover that your thumb points down, right? So what that means is that reversing the direction of F, flip the direction of tau. Okay, so please try not to give each other the middle finger as you're doing all this, but also please be nice to each other if it happens. Please forgive your classmates if it was clearly an accident. Okay, yes?
So, with a problem, would we be given like the first two vectors, for example?
Yeah.
Define?
Yeah, so if you are asked to figure out the direction something points and you're told two other directions, okay, then if it's a matter of like pictures, right, then you would figure it out using this algorithm.
Okay, it's like. Okay.
Does that make sense? But yeah, so to be honest, if you know any two of them, you can figure it out, right? Because if you know who is who, namely, your pointer finger is the first vector, your middle finger is the second vector. The product of those two in that order is the third one. So even if I only told you the first one and their product, you could figure it out by just holding your hand like this. You see it? And twisting it around until we figure out who's correlated with who. Does that make sense? Okay, you got a question?
So, as far as I understand, the best use of this is in conjunction with the magnitude report, just to figure out the sign.
Yes, it's to figure out the sign, but also which direction it points. I mean, a quick cheat sheet is that it's got to be a direction that's perpendicular to both vectors, but the question is which direction is that exactly, and that's what this is for. Yeah. Yes?
This isn't really related. I was just wondering if the equation sheet for the exam is out yet. I was wondering if the equation sheet for the exam is out yet.
I haven't shared it yet because we are in the final stages of arguing about the exam problems, and that argument affects what's on the formula sheet. And I am hoping that during this class I will hear back from Professor McLeod. We will be done with it, and I can share the formula sheet. So I will share it very likely later today, like with very high likelihood, because we obviously have to get the exam printed. Other questions? Okay, none of this is my slides. I sort of decided to make it up at the last minute, so, okay. Okay, we've talked about static equilibrium a bunch. We've talked about horrible things like ladder problems. What I want to do now is to talk about what happens when equilibrium fails. It occurred to me that I never did the demo for myself of whether banana peels are actually slippery. Are they? Has anyone tried this? I've never actually tried it. Maybe I'll try it at home. Okay. So hopefully, oh yeah. By the way, I stole this from the internet, and this was the standard logo for some slip and the copyright is Scottsdale Slip and Fall Touring from somewhere in Arizona. Okay, whatever. So let's talk about what happens when equilibrium is lost. Well, then stuff moves, right? But it's an interesting question to ask, how, right? Because when equilibrium fails, something could slip, it could slide, and those things are pretty much the same. It could roll, it could fall, like all kinds of stuff can happen. So like, well, which one actually happens? Can we figure that out? And believe it or not, we can. It's actually not even that hard. Okay, so that's what I'm going to explain today. And it gives me a good excuse to introduce just some useful examples. So, for example, suppose you have a box. There it is. It's on the floor. And you pull on it, or for that matter, push on it. It doesn't really matter for what I'm asking. Does it slide, or does it tip over? Right? I mean, it's pretty clear that either one of these things is possible in general. So which one is it? So let's try to understand it. It will help if I draw things on the board, otherwise I'll go too fast. Okay, that's my box. It has a height L. It has a mass M. What other information did I have? Oh, right. And there's a force applied to it right here at a height H above the ground. And despite what the ground looks like, that's because I drank too much coffee, it's actually flat. Okay? So, okay. So first, to slide, okay, what we need is to pretend like we go back up 2 months, right? And we think about force balance. So for force balance, we just have the box, here it is. We pull on it with the force F, and the only reason it wouldn't immediately started sliding is because of friction, right? If there's friction, maybe it doesn't slide. So, hoping that one of these is not running out of ink. So, okay, so there is a force of gravity down. There is a normal force up. I'm drawing a free body diagram, idealizing the box as a dot. And there is a force of friction that might fight to go that way. Right? And the force that you would be fighting to get the box moving at all is static friction. And for static friction, the biggest that it can possibly be, okay, is the coefficient of static friction times the normal force. That's how big it is. And in this case, demanding that the box doesn't fall through the floor or go to space, you discover that N is equal to mg, so this is mu s mg. Okay, so that's the force that's fighting you as you try to get it moving. So, so the condition to slide, okay, is that the force you apply has to be bigger than mu s mg. So this is the sliding condition. Is it clear why? You've done these kinds of problems before, ad nauseum, right? By now they seem very easy. Back when you first did them, they probably looked hard. But I hope that by now this looks easier. Okay, what about tipping? So how do we think about tipping? So what's the condition to tip? I don't mean economically, I mean like tipping over, like in a box. So, well, the torque should not be zero, right? And I gotta say, when we look at this thing, if it's gonna tip, right? I might as well draw it again over here. Here's the box. It's gonna pivot around this corner if it tips. Does that make sense? And if it tips, what it's gonna do is it's gonna do that, right? So we might as well declare that's the positive direction, just because that's where it would go if it went. And so actually we can refine this condition slightly. If the thing is gonna tip, the torque, the net torque, somehow has to be greater than zero. Does that make sense? So if it was zero, that would be equilibrium, then it's not gonna tip. But if it becomes greater than zero, then it's gonna start tipping. And we're gonna think about the interplay between tipping and sliding, but we gotta quantify the tipping condition a little bit more. So the next thing that we need to do is, okay, so what are the possible torques in this game? So there is the torque due to the force F. So that one is not super difficult, right? Because here's the pivot on this diagram. So that is a distance h away from the pivot. And the vector would be that. That would be the r vector. And look, r cross f is the torque. In magnitude, it's just r outside theta. The angle between them is clearly 90 degrees. So this is FH. Does that make sense? Okay, so the slightly harder thing, I'm going to draw a fresh picture, is to ask about the torque due to gravity. So here's my box again. Here's the pivot point. Gravity tries to fight you, right, in getting it to tip. So gravity pulls like that. So, but gravity, remember, for the purposes of torque, you should think of it as acting on the center of mass. Let's assume the box is uniform. If I was carefully writing an exam problem, I would say so. So if it's a uniform box, the center of mass is in the center. So gravity pulls down like this. This is mg. So now we have the following challenge. We would like to calculate this angle, and then the vector from here to there is r, so we got over there, and then this is the force. Okay. So, if you stare at this thing for a minute, maybe you will convince yourself that theta is 45 degrees. The reason I say that is that this angle is half of this angle, which is definitely 90 degrees. So theta should be 45 degrees. And then we need to know this length. Okay, so the side lengths are L. So that means that if I have a triangle which is L over 2 and L over 2, L over 2 here, and L over 2 there, I need to know the hypotenuse. Okay, so Pythagorean theorem to the rescue, I hope. Right, so we're going to do L over 2 squared plus L over 2 squared. That should be the hypotenuse squared. Okay, so what do we got? We got a quarter L squared times 2, because there's two such things. I gotta take a square root, and that will give us the hypotenuse. So this is 1 over square root of 2L is equal to the hypotenuse. Y'all buy it? Okay, so now we can write that the torque due to gravity is mg times 1 over square root of 2L sine of 45 degrees. Oh boy. So sine of 45 degrees, this thing, is square root of 2 over 2. To be clear, on an exam, you have calculators, feel free to just get it as a decimal number. But if you know a few different sines and cosines for certain angles, this is one of them that you might have learned in a long ago class. So I can simplify this a little bit. So we get mg right? Yeah? Good. Thank you for keeping me honest. Hopefully I got it right. So up there I didn't bother simplifying it. So let's see what that did on the next slide. Okay, so what are we doing, right? We're trying to figure out, does the box tip? We're trying to get a condition for that. Just like we had a condition for sliding. Same business, it's just in the slide, which I'll try to update the notes with. And okay. So the last thing that we got to deal with before continuing is, what about the normal force? So, well, think about it this way. If the box, let me redraw what's on the board. Maybe over here. See, if the box is almost about to tip over, imagine for the sake of argument that it kind of looks like this, where there's a tiny, infinitesimal amount of room over here, which is so small you can't really see it if you're in the front row, let alone in the back row. So what will happen is that just when the box is about to tip over, which is what we're interested in, it's resting on this point. Does that make sense? This is generally not true. I mean, in general, if the box is sitting there on the ground and it's not about to tip over, I mean, the normal force is distributed all on the bottom, and it's kind of complicated. But if the box is just about to tip over, then the entire normal force is coming up from this point, because everything else is not really touching. It's almost touching, but not quite. And so the normal force is going up like this. But this is the pivot. And the normal force is therefore applied at the pivot. So the normal force doesn't give a torque when the box is about to tip. So this is good because, let's look at our free body diagram. So we figured out the torque due to gravity, we figured out the torque due to the force that we are pulling with. We've figured out the torque due to normal force, it's 0. What about the force due to friction? Same comment as for the normal force, right? Just when it's about to tip, friction is pulling you that way. But the only place it has to act is at the pivot. And even if you don't think about it that way, friction is always that way, right? Which is always directed through the pivot. So, so that means the only two forces we got to worry about for tipping are gravity and the force we pull with. And so, despite how much I've been able to cover the board with scribbles, it's all not that bad because the net torque is FH minus 1/2 mgl. And we want this to be positive. So that means that FH needs to be greater than 1/2 mgl. So F needs to be mgl over 2h or whatever. Okay, so this is the tipping condition. I'm putting it in a box to be clear, not because you should memorize it. You shouldn't bother. And just because, like, we just got the tipping condition, we had the sliding condition. And so now, well, you can figure out, given a particular US, you can calculate the tipping force, which is over there, and you can calculate the sliding force, which is over here, and compare them. And you can see which is smaller, right? So, or which one is bigger. So basically, as you increase your pull, like if the sliding force is smaller than the tipping force, it's going to slide. If the tipping force is smaller instead, it's going to tip. I don't know if that makes any sense to you. Okay. By the way, if the box just wasn't tipping at all, if we're just kind of sitting there, then the net torque would have to be 0. And then there would be a force, a torque from the force you pull with, a torque from gravity. Those would be the same as what we did. And well, the friction can't possibly contribute to the torque because it's always directed along the line, along the same thing as the radius direction in this case. And so you would get this equation. And now you could solve for the normal force. But it wouldn't be very interesting. You could do it, but it's just not that interesting. Anyway, if you compare, what is it? The sliding force and the tipping force. If you wanted to tip first, for example, you want the tipping force to be less than the sliding force. Does that make sense? Like you pull a little bit, a little bit, a little bit. Whichever force you hit first is the one that's going to win. It's either going to make it slide or tip. Okay? And if you set up the inequality that involves, basically that's the statement that the friction is big enough. Right? And you need, like, imagine that you pull from the bottom. You pull somewhere here. That's gonna be more likely to make it tip, right? For any given amount of friction. Or to say it another way, if you do something like pull, no wait, never mind. I misspoke. Sorry. pulling from the top is the thing that's more likely to make it tip over than from the bottom. Does that make sense? Okay. So, okay, the next thing is something else. So, before I continue, any questions about things tipping over? Yes, in the back.
Why do you get it from the top to the bottom?
Please say that one more time, I didn't hear.
Why do you get something from the top to the bottom?
Okay. So the question was for everybody, why is it easier to tip something by pulling here as opposed to there? That's your question. Okay. Basically, the torque due to gravity is always the same, right? That's the thing you're fighting. So the bigger torque you can apply, the better your chances of tipping over, right? So the question is, where do you get the biggest torque? So here's the axis. So the further from the axis you apply your force, the bigger your torque. And that's why it's easier to tip something over if you pull or push on the top of it. Think of it this way. Imagine you are in the midst of rearranging your room, and you have a bookcase, and you want to move it, and you don't want to unload it with books, right? So it would be really bad if it fell. If you just stand near it, okay, and if it's freestanding, hope not, but if it is, and you just randomly push somewhere near the top, it's probably going to fall over. That's because you're pushing far away from the pivot point, which is on the floor. If you want to move a potentially tippy object, and you push near the bottom of the object, you're applying a force very close to the pivot point, to the would-be pivot point, so the torque that you're applying is very small, but as far as sliding is concerned, if you want to slide something, that's fine. Sliding doesn't care whether you apply the force at the top or the bottom. Does this stuff I'm saying making sense, or is it all very fluffy? It makes sense? Good. Yes? So, okay, let me do it on the board and make sure that I didn't screw anything up. Okay, so here we have a tip first. So for tipping first, we need the force for tipping to be less than the force for sliding. Like so again, I mean like for the critical force for tipping versus critical force for sliding. Does that make sense? So let's plug them in. So for the tipping, I can't read. It's over there, hopefully correct. So it is mg L over 2h, right? And over here, that is us mg. So let me try to simplify this formula. That's what you're asking about, or not? Whether I simplified it correctly? I'm getting nervous that I'm about to explain something you didn't ask about.
So up here, tau net equals force times height minus m.
Yes. Where would be?
Oh, I see.
This sentence. Okay, that handwritten sentence is not correct. No, you see this handwritten sentence is not correct. The correct thing is to put an H there. It's a typo. You see, it fails dimensional analysis. mg is a force, F tip is a force, L is a length. You can't have something which is force times length be compared to something which is a force. It doesn't make any sense. But if you correctly do the arithmetic from here to there, you would discover there's an H downstairs, which is also a length. So they would the units would cancel out, and then it makes sense. So there's a typo, it should have been 2H. And when I read it over here, I wrote it correctly with the H. It was a typo, so you copied it. No, not your bad. Please, I mean, I bet you like 20 other people were super confused about that, so I'm glad you asked. No, so F slide is this one. So let me label the board the same way I did over there. So this is F slide. And this thing here is F tip. So you could say that F tip is this. This is the critical value for tipping. And this is the critical value for sliding. So that is to say, if the force that you apply is a little bigger than this, it's going to slide, all things being equal. And if the force you apply is a little bit bigger than this, it's going to tip, all things being equal. But of course, which one actually happens depends on which one you reach first as you increase the force. Does that make sense? Okay. And then let me try to do this arithmetic on the board, make sure I'm not lying to you. So the mg's cancel. So what? Okay. So mu s is bigger than L over 2h. Okay, wonderful, whatever. Okay, so I'm just checking that I didn't have any other horrible typo on this slide. So it looks like the only nasty one is there should be an H next to the 2. Thank you. Other questions? Okay. Let me just back up and summarize. So this is, like, the tipping problem is kind of satisfying, at least for me, because it contains in it basically almost all of the ideas we've done in this class, right? It has the idea of, well, what does it take to get something to move? Like by pushing on it, right? It's got that part of it. It has the idea of what does it take for something not to move? It has the idea of what does it take to get something to rotate or not rotate? And it's all happening in a situation where you do not have a gazillion complications like with ladder problems, which you, by now, are all experts on, but you know, they're kind of hard. So hopefully, now that you've seen this, you are feeling like experts on these kinds of problems. If you don't feel like this is understandable, please ask. Okay. So the thing that I want to say now is you cannot quite always ignore the normal force. It is important for some problems. So there's a lot going on here. I don't really want to discuss every single tiny step. Just want to give you some quick overview. So imagine I was trying to, for some reason, hang a rod by attaching it to a wall in the way that's indicated, okay? So I have an angle theta, there's a tension in the rod, the length of the stick that I'm hanging is L, and I can work out the conditions for equilibrium, okay? And I would do that by figuring out, for example, the net torque, which has to be 0. So I figure out the contribution from the tension, here it is. I figure out the contribution from the force of gravity, there it is. To be clear, I'm now pointing at equations instead of actually doing it in front of you, so I'm not actually expecting that you, in a flash, see why it is obvious that this is what it is, because it is not obvious, you have to do the calculation. But I've done this kind of thing before, so I'm not sure it's that useful for me to do it again. But all I want to point out is that now, if you really want to get force balance straight, when you have to also make sure the forces cancel. And have to cancel in the x direction and the y direction. And for that question, the normal force from the wall is very important, because if you didn't have the wall pushing back on this thing, it would just go that way. And so when you write out the condition for the forces in the x direction to cancel, the normal force does appear, and you could figure out what it is. Okay? So you could calculate it. You should feel comfortable doing such things. But for example, for tipping, the normal force is just irrelevant. Okay. Any questions about this? This is just to say you can calculate normal forces, not you should instantly write all these equations without any further analysis. By the way, if you want to learn how to do these things, feel free to try to reproduce these equations. I think they're correct. I'll post these slides. Okay, so there's another situation in which things might tip over that is worth talking about. And that is if you have a box on a slope, right? So does it slide or does it tip over? Well, okay, so you have your slope, it's a hill, you put a box on it, gravity pulls it down, you just like let it do what it wants to do. And so the thing to realize is the only thing that could possibly make it tip over is gravity. Right? I mean, maybe gravity somehow makes it tip over, but why? Okay. Well, so the first thing that we can do is, let me do it in front of you. Okay, here's the normal force. Oh, sorry, no, here's the force of gravity. So the normal force is like that. So let me think for a second. So the normal force from your long ago inclined plane manipulations is mg cosine theta, right? Y'all remember that? And then the force along the inclined plane due to gravity, that is the force down due to this part, that is mg sine theta. I hope you also remember that. Again, from your long ago problem sets and exams. And then the force of friction due to static friction, the biggest that it could be, the thing you have to actually fight, is mu s times n in magnitude, so this is mu s mg cosine theta. And so what you are left with is, for sliding, the condition is that mg sine theta has to beat the best that friction can offer. So hopefully I can do this now. So, okay, so the mg is canceled. So when I divide through by cosine, I'll get tangent. So basically the angle needs to be big enough, right? And how big it depends on the friction. Does that make any sense? Okay, that's what I do in this slide. Now, what about tipping? So now there's something funny, okay? Because it might look like we're about to do a difficult calculation, but we're not. We're just going to draw a picture and realize you don't have to do anything. It's just the answer is kind of staring us in the face. So imagine you draw a picture of what's going on. So here it is. I'm kind of zooming in on the box itself. So if it's arranged like this, and the normal, and the force of gravity comes down like that, for it to tip over, the force of gravity has to not be balanced by something. Do you understand that? So right now, the torque due to gravity is trying to pull the thing into the hill, but it can't go through the hill. But if you keep increasing the angle, at some point the downward vector that's describing how gravity pulls it down is going to miss the hinge point. Do you see that? As soon as that happens, there is a torque due to gravity. that isn't canceled out by like normal forces and stuff. Do you see that? So you gotta worry about this. And if you think for a little bit, what's the magic angle here? It's 45 degrees. Okay, so why is it 45 degrees? That's a fun, well, maybe I'm a weirdo. Okay, it's a fun geometry problem. Let me explain. Because what you want is the following thing. So here's the center of the box, and you want the force due to gravity to the critical force would have to go to the through the corner. So it has to look like that. So tip this thing like this, so the picture would look like that. Here's the center, and it goes down like this. But it's easier to look at it when it's like that. So this angle in any rectangle is always 90 degrees, and this has to be half of it. It's gotta be 45. Okay, so basically, if the angle of the slope is greater than 45 degrees, you tip over. If it's less than 45 degrees, you won't tip over, and you may or may not slide. Depends on the friction, right? But if the angle is greater than 45 degrees, there is nothing friction can do for you, for the box, if you were the box. It will tip. There are possible consequences of people who ski, but I'll leave that to the readers. Okay. I really want to say anything about car handling. Let me just say very briefly, okay, the reason that like fancy race cars that have to turn in really tight corners tend to be very low to the ground is that all the forces that might potentially have made them tip over are applied very close to the ground, which is where the tipping point would be, the tipping axis. And so they're hard to tip over. That would be really bad if your car tipped over. And if you have a thing like that, there are benefits to that, but resistance to tipping is not one of them, right? Because the center of gravity is pretty high, and as you turn, you might have forces acting on the car that might make it tip over pretty easily. Okay, I in principle have 2 minutes. I was going to start talking about gravity and Australia and kangaroos and so on, but I can't really do justice to kangaroos in 2 minutes, so I'm going to shut up here.